Before, we saw that you can include information from a sequence of data using a recurrent connection on the hidden layer. This connection goes through these weights, WHH. If we unroll the network, we see that the hidden layer at step T is a function of the previous hidden state multiplied by those weights, and the output from that layer is again multiplied by WHH. For every step you have in the network, you're multiplying by the weights again and again, and when you're doing backprop, that's even more multiplications. This leads to a problem where the gradients going through the network either get really small and vanish, or get really large and explode. This happens because if you're multiplying by some number a bunch of times, you're gonna get two results, except in a couple special cases. If that number is less than 1, you'll end up at 0. If it's greater than 1, you'll head towards infinity. This happens to gradients in a normal RNN. They'll either vanish or explode. This makes it difficult for RNNs to learn long-range interactions. Luckily, there is a solution. We can think of recurrent networks as a bunch of cells with inputs and outputs. Inside the cell, you have your network layers, such as the sigmoid layer labeled with a sigma here. To solve the problem of the vanishing gradients, we can use more complicated cells called long short-term memory, LSTMs for short. Okay, LSTM cells are pretty complicated at first glance, but if you break it down into parts, they aren't too difficult to understand. The key addition here is the cell state labeled C. I'll get into this next. In this cell, there are 4 network layers shown as yellow boxes, each of them with their own weights. The layers labeled with sigmas are sigmoids, and tanh is the hyperbolic tangent function. Tanh is similar to a sigmoid in that it squashes inputs, but the output is between -1 and 1 instead of 0 and 1. The red circles are pointwise or element-wise operations. That is, they operate on matrices element by element. The main improvement here is through the cell state. The cell state goes through the LSTM cell with little interaction, allowing information to flow easily through the cells. The cell state is modified only through these element-wise operations, which function as gates. And the hidden state is now calculated from the cell state, then passed on. The first gate is the forget gate. The values coming out of the sigmoid layer are between 0 and 1. Then they are multiplied element-wise with the cell state. So values from this layer close to 0 will shut off certain elements in the cell state, effectively forgetting that information going forward. Conversely, values close to 1 will allow information to pass through unchanged. This is helpful because the network can learn to forget information that causes incorrect predictions. On the other hand, long-range information that's helpful is allowed to flow through freely. The next bit updates the cell state from the input and previous hidden state. The tanh layer output is added to the cell state, again gated by a sigmoid layer. In this way, the cell state can be updated in the step and passed along to the next cell. Here, the cell state is used to produce the hidden state, which is sent to the next hidden cell, as well as to higher layers. It's the arrow pointing up here. The cell state is passed through another tanh, then gated again with another sigmoid layer. All these sigmoid gates let the network learn which information to keep and which information to get rid of. Putting all this together, the LSTM cell consists of a cell state with a bunch of gates used to update it and leak it out to the hidden state. This is just the basic LSTM. There are multiple variations and a lot of ongoing experimentation into improving these. They are also easily stacked into deeper layers. You just send the output from one cell to the input of another. Okay, so now you might be wondering how all of this fixes our gradient problem. Since the cell state is allowed to flow through the hidden layers with only this linear sum operation, gradients can easily move through the network without being diminished. You also get gradients added into the network through the LSTM cells, but they are just added to the gradients flowing through. I'm not going to get into the math behind all this. I'll link you to some resources, such as a great lecture by Andrej Karpathy, to help you out there. LSTMs are the basic unit of recurrent networks these days. You don't have to completely understand the inner workings, but knowing how they work conceptually will be important.